Okay, so let's continue from last week. Basically we ended at the linear transformation. If a transformation or a function satisfies 1, 2 here, then it is called a linear transformation.
Yeah.
Okay, and last time we've seen an example, and after testing, we found that it is actually a linear transformation. So let's start from another example. Say I got a okay, I have a transformation t r squared to r squared. And this transformation is defined by if I have an input xy, I transform it to no after transformation, it will be equal to x plus 1 y. Okay, now I have two vectors. U is 1, 1. V is 2, 2. All right, so now let's check these two equations. So first, t of u plus v equals t of 1, 1 plus 2, 2 is 3, 3. And that will be equal to 4, 3. All right, and then t, that's my left-hand side. And then my right-hand side equals t of u plus t of v. All right, t of u is 2, 1. T of v is 3, 2. After adding, I got 5, 3. Okay. Now I have 4, 3 for my left-hand side. I got 5, 3 for my right-hand side. So this time, my left-hand side does not equal to the right-hand side.
So it's not.
So that means equation 1 does not hold. And that means T is not a linear transformation. Okay, so there is another thing you can check, like so if you've done the rotation matrix, let's say there is another transformation also from r squared to r squared, and we say there's a transformation matrix is to rotate by angle theta, and theta is radians. Counterclockwise. size. About 0, 0. So such matrix looks like the transformation of a vector v1, v2, it equals v1 cosine theta minus v2 sine theta. v1 sine theta plus v2 cosine theta. And the question is to check if this is linear or not.
Mhm.
So you can take like 5 minutes to do this question and tell me if it's linear.
Okay. Maybe you want some fruits? It is a linear
It is
transformation.
linear. Perfect.
Yeah.
Nice. Okay, so so you know that for linear equations we have two equations to check. For linear transformations we have two equations to check. But there is a proposition saying that we can check one. We can have one equation combining those two. So
Okay.
there's a proposition for transformation V to W. V and W are vector spaces as linear means for all V W belongs to V, let's say VU. And scalars. So this equation is transformation of alpha U plus beta V equals alpha transformation of U plus beta transformation of V. So this is just like a combination of these two. First, we have a vector addition, like the addition of vectors, and second, we have the scalar multiplication of vectors. Okay. And remember, if we prove if and only if we would do the both sides. Right. So another proposition for all linear transformations, if a transformation from V to W is linear, then transformation of the zeroth vector is the new zeroth vector in the vector space W. Okay, but this is only like a single direction statement, so it cannot be inverse. Say the transformation of a zeroth vector is zero does not mean it is linear.
Mm-hmm.
And we can prove based on the first proposition we have. So we have a linear transformation, then it means that T,
But the inverse isn't true, right?
right. So back is not true. So by um, by linearity, we have T of zero equals T of 0 plus 0, and that's by the additive identity, and that equals T of 0 plus T of 0. And T of 0 itself is also equals 0 plus the T of 0. So from here we have, if we subtract t of 0 on both sides, we have 0 equals t of 0.
Mhm.
But remember, this first 0 vector inside is in the vector space V, and this one is in the vector space W.
I see.
Great. Um, okay, now let's mm, so after introducing the transformation of the of a vector, any vector, so we say that if we have a transformation from Rn to Rm, if we know this is linear, and instead of knowing what's the transformation of any vector v1, v2, we know that how the transformation is like of the basis. That's t of e1, t of e2, all the way to t of en. Then we can complete the transformation. C of any v in Rn. So this proposition is saying that every linear transformation is determined by what it does on the basis. So all linear transformation determined by what it does on the basis. So if we have a vector v in the space Rm, so for vector v equals Rn, so v1, v2, all the way through vn. All right, this vector belongs to Rn. So basically, v can be rewritten as v1 times e1 plus v2 times e2 plus da 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 plus vn. So remember e1, e2, and en is the standard basis. So e1 is 1, 0, 0 all the way to within minus 1 zeros. E2 is 0, 1, 0, 0 all the way to 0. And
Can
en.
a vector space have more than one basis?
Yeah, there could be multiple bases. But if we know the transformation for standard basis, then we can write the transformation as a matrix. But if we know the transformation for like other kind of bases, we can also compute the V. Okay, so right now I have the standard basis, and basically if I have a transformation T of V, that's basically T of E1, E1 plus da 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 plus Vn, En equals, by linearity, we can just take the scalars outside. So it'll be V1 T of E1 plus V2 T of E2 plus all the way to V and T of E. So if you have other kind of bases, you'll just have like V1 equals something like this. V1 would be something else, like with a lot of V's, like V2, V1, V2, V3, with some scalars like that. We've seen examples before. But we can still rewrite the how do we represent each V, or how do we represent each entry of V.
Because I thought
Mm.
V1 or
Mm.
V2 is like a singular, is a single, like a single value. Like it's
Yeah,
not, right?
it is in this case.
So if V1 is a singular value, like
Mhm.
V vector 1,
Mm.
um, then how can V1 be equal to V1 times E1 when E is a vector
Well,
that has n many elements?
I mean, like, if we have another basis, like here, if we have some kind of, I don't know, alpha one instead, and then this place would be something like V1 plus V2 and something else. And this is also a scalar value because these numbers are. For example, instead of like, in this case, if V1 equals 1, then here it could be some uh like 11 or something.
Yeah, I understand that part. I feel like because E1 is like 1 0 0 0 at 1 and n minus 1 zeros, right?
Mm.
So given that E1 itself is a vector,
Mm.
how does a vector times a scalar become a scalar?
It's a vector.
I lied.
Uh, Right. This is like after multiplication, for example, I'll have like V1 times E1, I would have a V1 0 0 here. And E2 is like 0 V2 0 0 0
Oh,
here.
and then you add it together. Okay, I see.
Yeah.
Okay, never mind. Okay.
Okay. So if I have a transformation with all these places, we would have this equation by linearity right here. Okay, now see an example. If I have a transformation from R squared to R squared, and I know that T of E1 is T of 1 0, and that's 2 3. And I know that T of E2 is T of 0 1, and that's -1 4. Okay, now I want to find T of 3 -1. So we know that 3 -1 can be written as T of, so 3 times 1 0 plus -1 times 0 1. Right. And now we can rewrite this equation by linearity. That's 3 times T of 1 0 minus 1 times T of 0 1. So that would be 3 times 2, 3. It's right here. And similarly, plus uh, next. All right, now this would equal to right, 6 plus 1, 7, all right, 9 minus 4, 5.
Mhm.
Okay, so this is my um result for this transformation. All right, now why this is important in linear algebra? It's because basically if we know T of E1 is 2
Mhm.
3, and we know that T of E2 is -1 4. This basically tells us that we can write this as a matrix. So we write matrix as T of E1 is 2, 3. T of E2 is negative 1, 4. And this transformation of V can be written as the matrix times the vector V. And in this case, this matrix is the matrix right here. So we can test this times V. And in this case, my V is 3, 3 negative 1. It's right here. So for matrix multiplication, it's 6 plus 2. Wait, 6 plus 1. Minus 4. That's 7, 5. So we got the same answers. Okay, so this can be simplified to or generalized to a important theorem. So I don't know if it's a theorem or proposition, but here it is. So if I have a transformation from Rn to Rm, we only need to know the transformation of the basis, T of E1, T of E2, all the way to T of En. So if T of E1 equals A1, T of E2 equals A2, all the way to T of En equals An. And then we can just put the column in the matrix. I would have a matrix A, and A is n by m. That equals, the first column is A1, the second column is A2, all the way to the nth column. Okay, so we know that this transformation is from Rn to Rm. So basically all these vectors has m entries and they belong to Rm. So then there are m rows and n columns. So this dimension is n by m. N by n.
Rn to Rm.
Rn to Rm, yes.
And you have, in each column, you have m number of elements and n columns. Okay, makes sense.
Yes. So A1 is like A1, A2 through AM. Okay. So if I have this transformation and I know these bases and I can write this A, basically it means that for any transformation T of V, you can write it as A times V.
Mhm.
And this A looks like this.
Yeah.
Okay, now let's now there's another definition. So for a matrix notation, A times V, that equals the sum of VK K times AK. Oh. So K from 1 to N. Okay, now AK is the kth column of A, just like here. And this VK is the kth entry of V. And basically this sum means when we calculate, we can do so VK from 1 to N. So we start from V1, A1 plus V2, A2 plus all the way to VN, AN. Okay, for an example for this definition, if we were to calculate 1, 0, so 1, 2 times 2, negative 2, 1. So this is my matrix A, this is my vector V. And we know that this matrix A is 2 by 3, this vector V is 3 by 1. So you might have already know that we are expecting a 2 by 1 matrix.
Yeah.
Right. So when we calculate before, we're doing like these three multiplied by that is my first entry, and the bottom three multiplied by that is my second entry.
Mhm.
But so basically for this linearity, we know that what we're doing is basically the first the first value in the V times the first column in A, and then the second value in the V times the second column in A. So if you think of like in as a transformation of a basis. So this time we can calculate it as 2 times 1 negative 1 minus 2 times 0, 5 plus 1 times 3, 2. This gives us the same thing. So 2 plus 3 is 5. And next to subtract 10 plus 2 is 10.
Is it minus 10?
Plus 10, I think. Wait. Oh, yeah, right. Attach. So this is just another way to do the matrix multiplication. Sometimes it's easier than the other one. At least it's more clear.
Yeah.
Right. So then there's another definition. So if I have row vectors, so let's R equals R1, R, R2 through Rn. So let R be a row vector. And C be column vector. C equals C1, C2 through Cn. Then the dot product of them.
Does it only work for column and row vectors?
Yes. Okay, so basically, if we have a row vector and a column vector after the dot product, we will just have a scalar. Or like this number will just be a constant that belongs to the R space. So actually, when we calculate AV, the kth entry is the so the kth entry is the kth row dot product with V. So that means for how we calculate before, we find the row and we find the column and we do like 1 times 2 plus 0 times -2 plus 3 times 1. And that's actually how we calculate the dot product. So
Kth row Oh yeah,
Yeah.
because V is a column vector.
Right. V
Okay.
is the whole column vector right here. So this is actually control of A. All right. Now there is a notation that we usually use. Uh, so if we have a matrix T V equals AV, then the matrix associated with T, in this case A, we often write it as this bracket T. Or sometimes we just write T.
Oh, that's confusing.
Yeah, right.
So does that mean no one? So if you have this notation, does that mean that people don't really use the linear transformation, the other
Um,
notation? They just write it as a matrix multiplication?
yes.
Okay.
Okay. Mm, so then we have a mm, then we have another definition. So if again B and W are vector spaces, let L of VW be all the linear transformations from V to W. Hmm. So so this L contains all the transformations. So if I take two of them, if I have a transformation S and T belongs to this set of L, then we can define S plus T.
And S is just a random transformation, right?
It's also linear.
Oh, it's also linear.
Yeah. So S plus T of V equals S of V T.
Wait, this is random, but if S plus T So if S and T are both linear transformations, isn't S plus T contained in L? Because S plus T should also be a linear.
Exactly. Good. So this is information. So L is like all every linear transformations, and S and T are in L means S and T are both linear transformation. All right, so this is the first definition, S plus T. And then we have another definition on the scalar multiplication. So if T of if T belongs to L, then we let and alpha is a scalar. Then we define alpha T of V equals the alpha after multiplied after the transformation. Okay, now we have defined S plus T and the scalar multiplication. So that actually remind you of the vector space, and the theorem we're introducing is is that this L of VW is a vector space.
So okay, so since it's a vector space, what are the vectors in the vector space? Is it just like if anything that's in all the resulting matrices? I mean, not matrices. All the like results from all the transformations.
Yes. So in this case, if we say this L is a vector space, then this vector space includes all the linear transformations from V to W with these two operations defined. So remember, vector space is defined by
Addition and scalar multiplication.
yes. Oh, it's right here. So it's defined by these 8 axioms. So first is closure, then we have additive properties, we have multiplicative properties. So as long as a space or a set satisfies these axiom, then we call it a vector space. For example, we know vectors like Rn is a vector space, but Rn also include like just this R. So all the real number is actually also a vector space. And I think all the integers is also a vector space. Like if we define the scalars to only be integers.
So then like what's not a vector space?
the
I guess you just make something up and then test it, right?
uh,
I think you
right. Yeah. Oh,
yeah. You give an example before.
yeah, I think.
Yeah.
Yeah, but like if it define the operations to not be like to be not held by those axioms, then it's not a vector space.
Oh, so if you make it like x plus is like x divided by y, then it's not going to be
Mm, right.
like
I can
v.
verify
Yeah.
that, but yeah, if like for example it does not hold in for the commutativity or the uh like matrix not matrix multiplicative distributivity, then we say it's not a vector space. So basically,
Mhm.
to say this is a vector space, we need to check the axioms.
Yeah.
So for example, what you have already said is additive closure. So S plus T, for example, is closed because S plus T is also linear, is also a linear transformation defined on V to W. But to verify it's linear, we do that T of alpha V plus beta U stuff. And we verify the equation. So right now we have a S plus T of V. By definition, we know that A equals S of V plus T of V. That's this definition of the operation. And this whole thing belongs to W because S of V belongs to W and T of V belongs to W.
Mm.
So this whole thing belongs to W. Okay, now let's verify S plus T of alpha U beta V. Where V and W, where V and U belongs to this V. Mm, right. Now, by definition, this equals the S of whatever inside plus the T of whatever inside. And now we know that S and T are linear, so we can further rewrite this to alpha S of U plus beta S of V plus alpha T of U plus beta T of V. Okay, now I have alpha S of U, alpha T of U. So if we take the alpha out, we have S of U plus T of U. Similarly, we have beta times S of V time plus T of V. Okay, now we can use the the definition of S plus T again. So we know that S of V plus T of V is S plus T of V. So then in this case, for S of u and plus t of u, that equals S plus t of u. Similarly, that equals beta times S plus t of v. Okay, and this is just what we want to find. So basically, we've proved that S plus t of this thing equals alpha of S plus t u plus beta multiplied by S plus t of v. So then we know that S plus t belongs to this linear space L, space of linear transformations. Okay, similarly, we prove things like additive uh, commutativity, and distributivity, the associativity and stuff. Okay, this is everything for the basic linear transformations. So then we can move on to the composition of linear transformations. So very similar to the composition of functions, the composition of linear transformations also we write it as the okay, before that, let's define two transformations, T1, T2. Suppose we have a T1 map from R into Rm. And we have a T2 map from Rm to Rk. Okay, and they're both linear. All right, then we define the composition of them similar to the composition of functions. We write it as T2 composite with T1 of V. So that means we are doing T1 first and T2 second of V. So we transform V by T1 first and then by T2. Okay. So there is a proposition saying that if T1 and T2 are linear, then this composition is linear.
It's just like a comp. Oh yeah, because transformations are just functions, right?
Yeah.
Yeah.
So similarly, we can verify that with that alpha and beta stuff. I'll skip that. Okay. But what's important is if we have T1, T2, and this composition. So if I write skip to so if we have T1, T2 composite with T1, if I just write it as T, then there are matrices T1, T2, and T. Now I want to know their relationship between matrix multiplication. Okay, so define. If we have two matrices A and B, the entry in the jth row and kth column, we call it in jth and kth. Of the multiplication of AB is AB jth row, kth column. And that equals the row J of A times column K of B.
Mhm.
So we write it, we say AB jth row, kth column equals the sum of, so the jth row of A and each entry in the jth row times the kth column of B, but each entry of the column, and this each is iterated from 1 to n.
Is that the little e is a each?
Yeah, it's a L, but yeah, same.
Oh, okay.
So this is just how we write it, like with symbols, but the idea is just when we do the matrix multiplication, we do that row and column stuff.
Mhm.
So one, so this means if we do, so if we want to find the jth row and kth column, for example, if we say the first row and the first row and first column, then we just do, so first row first entry multiply second row first entry, second column first entry plus, because we're doing the sum, the next one, the next one. So it's just 5 plus 0 plus 0, like that.
And then
So the first one is 5, then we have next line 6, 8. So basically we know that for a matrix A, that's m by n. And if we have a matrix B, that's n by k, we would end up with a matrix AB that's, or the answer matrix is m by k. Right. So let's time is it? Right, we have time. So this is about matrix multiplication, and let's talk about some properties of matrix multiplication. So the first class we've introduced some things like associativity, distributivity, and scalar multiplication, I guess. But these are the properties of matrix multiplication. So if we have 3 matrices A, B, and C, where the product exists. So the first property is associativity. We have AB times C equals A times BC first. Second is distributivity. We have A times B plus C equals AB. And this is similar to A plus B times C equals AC plus BC. Okay, but this one, you cannot write it as CA times CB because matrix is not commutative. In terms of multiplication. Okay, T is scalar multiplication. So scalar multiplication is commutative. So if you do A multiplied by alpha beta, then it's the same thing as you multiply by alpha outside. You do A times B first, alpha beta, alpha B. Okay. Now, what's the relationship between the matrix multiplication and the transformation? So we have a theorem. It says if we have a T1 is this linear transformation, and that maps from, again, an Rn to Rm. Is linear. And with matrix A, and Similarly, for T2, it's Rm to Rk, I guess. Again, it's linear and associated with matrix B. Okay. Then we have that for T2 composite with T1. So T1 is from N to M, T2 is from M to K. So T2 composite with T1 is N to K.
N to K.
Great. N to RK. And that is associated with B times A. So basically, in this case, A is M by N. B in this case is K by M. So this times A would be K by N.
Wait, but if it's B times A, doesn't it become? Oh yeah, I'm done. Yeah.
Great. So similarly, if we go to the other way, like if we go back in direction, so another theorem. So if we have a matrix that belongs to a M by N matrix, like all M by N matrices, then the map T from Rn to Rm if this map T of V equals the AV with this V, then uh then the map T is linear. How can I write this better?
What's a map?
Map is like a transformation. So for example, map is if you map something from Rn to Rm, and for a function, so we define function as a map where one element cannot be mapped to more than one.
Oh, okay.
Yeah. So transformations or functions are a specific type of map. So map is like a big term, and then functions or transformations are inside of it.
And these and like the defining characteristic is that it's like a one-to-one map.
Not one to one, but so one to one is like one result cannot be mapped with two inputs, but function is one input cannot mapped to more than one output.
Okay.
Yeah.
But multiple can map to the same output.
Yes.
Oh, okay, gotcha.
Okay. All right. Um, it's linear. So we can do the proof for this by just so since A is the matrix associated with T, then we can prove linearity by verifying T of alpha V plus beta U by the matrix multiplication. So this T, since T of something is A multiplied by something, then A multiplied by alpha V plus beta U is by the property of matrix multiplication. So this is a scalar multiplication. This is alpha AV plus beta AU. And again, A is just T, so alpha T of V plus beta T of U. And we've verified the linearity. Okay.
Yeah.
So before we finish for today, yeah, did you try the software you were talking about? The for the Celtic knot.
Oh yeah.
Yeah, I think that one like um even if it works for Celtic knot, it will be hard if we want to do like the Chinese knot. So yeah, maybe we can just try from the with the handwritten indices with the Plotly or Matplotlib stuff.
Yeah. So the
Yeah.
main thing is training it to create so the main thing is like training it to take the image and like stretch it over a coordinate plane and then identify the points, right? That's the main thing. The
Yes.
crossover and edge points or
Yes.
border points. Okay. Because I couldn't even I tried to download the software, but then
Uh,
it was really I don't know, for some reason it just didn't work. So yeah.
right, right. I know, let's do those kind of input for now. Yeah. It'll be a lot easier if we can just do like the images of Celtic knots or Chinese knot, and then we do
Mhm.
like image classification, but